If you take bicycles, I don't know.
You're helping that.
All right, so we have 4 sections for this test. 4 sections that we're going to cover. You could definitely expect relatively straightforward questions for these topics because they were all pretty straightforward. There was nothing that was like tricky along the way. I'm not sure if this So let's start with 7.2, 7.3. What was 7.2 and 7.3 all about? We had 2 topics in there, really. 2 topics. What was one of them?
Circular motion.
Circular motion. What was the other topic? Which is in circular motion, yep. It's inside there. So centripetal force and tangential velocity is all in circular motion.
Kepler's laws.
Nope.
Oh, I thought you said
That was in 7E, which we're going to cover also.
What is 70 on the test?
Yeah.
I thought we were just having in general.
Wait, do we have?
No, right now I'm asking about 7.2, 7.3, I was saying, yeah.
Gravitational pull.
Yeah, force of gravity. And this was the universal force of gravity, remember? Between any 2 objects. So this was 7.2 and 7.3. This is 7E. And then finally the last part was what? We just did it. What did we just do? What topic recently? Torques, or torque. Very good. So those are the main 4 topics. In the circular motion section, we talked about a lot. We really did it. We talked about a lot. It was like 3 days long, the lecture. We talked about tangential velocity as opposed to angular. So we talked about, remember that example with the merry-go-round? Where an object further out on the platform actually moves at a higher tangential speed because it covers a longer circle. The object that's further out has to travel a longer circumference in the same time that the object in the inside travels, assuming that it's rotating as a fixed body. Like the ground, like imagine a merry-go-round that had lanes, then it wouldn't be true, right? If there were lanes and the outer horse went fast and the inner horse went slow, and the horses didn't like stay lined up and they staggered as they went through, then you couldn't say they had the same angular speed. But in this case, we were talking about the fact that what if a body that's fixed rotates? Well, it doesn't matter where you are in that body. So here's that object rotating. If you're out here, if you're in over here, the center is the X. Okay, no matter where you are, if this body rotates as one fixed object, no matter where you are, you have the same angular speed. Same angular speed. What does angular speed mean? How is angular speed different than tangential speed? Angular versus tangential. Anybody else? Only for this one? Angular versus tangential? Ben, is that a hand or you just kind of...
I'm going for it now. It's kind of like an application.
Hand, why not?
On me? Isn't angular speed things like rotations per minute while tangential speed is like velocity?
So remember angular speed had to do with the rotation. So if I'm on the inner track or the outer track, the object rotates in a minute at the same rate. So I rotate 1 revolution per some unit amount of time. So these 2 objects, ready? Here's what happens. They rotate like this, and they get back to where they started at the exact same time because this object is fixed. It's a plate, like a CD spinning, or a record player, like a record spinning. Okay, every piece of the record spins at the same angular speed. But this outer object covers a long track. The inner object only covers this little short path on the inside right here. So we could say that the inner object has a lower tangential speed. And that's measured in meters per second. But they have the same angular speed, which is measured in like degrees per minute or revolutions per minute. or rotations per minute, depending on what kind of object motion it is. So angular speed means, well, you know what? They both spin 360 degrees, and it takes them both a minute. They have the same angular speed. But the outer one travels further distance, so that has a higher tangential speed, the outer one. We went on to talk about the concept that how does an object stay in circular motion? Give me an example of an object in circular motion, but also tell me the force that provides the centrifugal force. Give me an example. You spoke, what were you saying?
I was just thinking aloud.
An object that moves in circular motion, and what provides the force?
Would it be like a satellite that goes around Earth gravity and
Exactly. Okay, a satellite that orbits the Earth, gravity is what's keeping it in circular motion. What else? Give me another example.
Something going over a loop would be a normal force.
Anything that goes in like a loop, why doesn't it shoot off? The normal force pushes back to keep it on track. Very good. What else? There were others. How about the lag we did? How about the lag we did? We had to spin on the stopper around.
Well, I don't know if this is the lab, but there's a pin. So something's coming out of the pin. So something's moving.
What was keeping it in circular motion though? What force?
Gravitation?
What was the scenario? I didn't really hear you.
Oh,
Was it a pen?
A pin, like a pin and a piece of wood, how we were talking about the wood, and if you spin the wood, but that's...
Oh, interesting. Like if you spun that wood and it just continued to spin over and over. I guess that would be. I guess that would be like normal force in that sense, because the wood wants to move outward, the bulb is pushing against this motion. Yeah. What about the lab though, with the rope or the cord? Yeah. What kept that in circular motion? It's not you. Remember, it's not you. Yeah.
The tension in the rope.
Yeah, the tension. When you spun that object, the rope was taut, meaning there was tension in it. The tension is what's pulling back. So the concept of what keeps something in circular motion, well, we have to also consider the fact that when something is in circular motion itself, so we're still on 7273, when something is in circular motion, there's a centripetal acceleration acting toward the center. Here's the object spinning like this. Let's say it's a planet going around the sun. We know it's not really circular, right? We know it's elliptical, but we're making the assumption for now it's something circular. So as this object goes around, it has to be pulled toward the middle. It has to, or else it goes where? Tangent to the circle. If for some reason the sun just disappeared and the planet was right here on the side, right there, it would shoot off like this.
What would happen to us?
If the sun just disappeared, I mean, our planet would go flying off into space. We might collide. We would lose heat. We would become an ice age. Pretty much die. But I mean, how long? Do you know how long it takes the sun's rays to get to us? Anyone know?
No, it takes like 7 seconds.
I was close to the 8.
5 minutes.
8 minutes.
8 minutes,
Yeah.
that's what I meant, not years.
It's about 8 minutes it takes the sun's rays to get to us. So if the sun exploded right now, would we know?
No,
How long would we know in?
8 minutes.
In 8 minutes.
Oh my gosh.
So you know what? You're seeing into the past. Think about it. The light that you're seeing was 8 minutes ago. It was 8 minutes old. It's kind of crazy to think about that. You're like technically seeing into the past when you see light. Okay, because that light started 8 minutes ago. It just took forever to get to you. Better?
I was saying, what about the moon?
What about what?
The moon, what if the moon just kind of left?
If the moon just disappeared, what would that affect? Anybody know?
Tides.
Tides. High tide, low tide. It's actually pretty big deal.
Oh my gosh, the tides. There's the water.
Yes.
What?
Thank you, Ali. It would affect the tides.
It'd be fine like Minnesota.
What?
It'd be fine in like Russia, like the middle of Russia, like China.
Sure.
Wouldn't it be lower tides? Or would it be...
But there would be no low or high tide, because low and high tide occur way based on like
I'm just going nuts.
the asynchronous nature of the moon. So you would just have like regular tides. There would be no low or high. It would probably be like somewhere in between the two.
Oh my god, the tide. You
But a lot of things happen with the tides, yeah. When the tides are low, a lot of people go and what do they do when the tides are low? No, you go clamming when the tides are low. When tides are low, all the clams are they're exposed. That's why the saying is happy as a clam in high tide. Did you know that or no? Ever hear the saying? I know, no one ever says that part. The saying is you're happy as a clam. At high tide is the end of the saying. Because at high tide, the clams are all covered. The tide comes up and it's high water level. But when it's low tide, the water recedes and all the clams are exposed and people go around and take the clams.
Can you do one of the homework problems from 7E?
From 7E, sure.
Yeah.
Do you remember which one?
Yeah, I have it. It is the first one. It says, a planet's mean distance from the sun is 2 times 10 to the 11 meters. What is its orbital period? And then it says, use the numerical information about the Earth from the table after Kepler's third law.
Okay. So, I'll go back to 7.2 and 7.3. Let me just answer this question. So the question gives us the mean distance from the sun as r. The question says, what is the orbital period? Okay, what is the orbital period of this planet? Well, here's the problem. You can't do this unless you have some other sort of information, which you do though. That's why I put use the data from your notes. So if you look at your notes, all you have to do is look at your data table. So tell me please, for the Earth, what is the mean distance? It's on your notes. Take a look.
1.4957 times 10 to the 11.
And how many seconds does it take for the Earth to revolve around the sun?
3.156 times 10 to the 7.
So these are the data points or data values from your table in your notes. So if you need to see where this is, it's in 7E in the notes. This is the Earth's data values. For all planets, what is the ratio that is held constant? For all planets, what is the ratio that is held constant? What is the ratio that is held constant? What do you got?
I was just stretching.
That was not even an answer, that was just you stretching?
Yeah, so it was like
Can I finish? 6.67 times 10 to the 11.
6.67 times 10 11. That is the universal constant of gravity, yes. But our question is, what is the ratio that relates the orbital period and the average distance? Is it what? It doesn't, if you use the second data table, we ended up getting 1 for all of them, but not here.
T squared over r cubed.
Yeah, so what you have to do here is think about the fact that you need to look at the time period squared over the average distance from the sun cubed. And that is a constant ratio for all planets. So just set that equal to the same thing. For one of these, take this r for the Earth, plug it in right here. Take this time period for the Earth, plug it in right here. So that's one side of the equation, the Earth. On the other side of the equation is the other planet. Well, you know the R value for the other planet. It's given to you. The R value for the other planet was given to you. So take that R value for the other planet right up here, plug it in all the way down here, and then solve for what I'm circling here. So you know R for the Earth, plug it in here. You know the time period of revolution for the Earth, plug it in here. Now, Katie was using the time period as 1 year. She was saying, right, let's call this 1. And then Katie used 1 astronomical unit, AU, for the distance. But that was not given in astronomical units, so you can't really use it because the units don't match up. Okay? So we're going to use meters and seconds for this. I will give you the data on the test. You will not go without data. You'll be given some sort of data. I can give you that data in years, in seconds, in meters, whatever it may be. But whatever data I give you, use that data value. And then we solve for t. Okay? And then we solve for t. So plug in for those 3 variables you know. Solve for t squared and then take the square root of both sides. This is a good math question you could definitely expect to see. Okay? What's the difference between revolution and rotation?
Well, like, the Earth revolves around the sun.
Good.
It rotates on the axis.
Good.
So it revolves and rotates.
Yes, it does both. The Earth is rotating on its own axis as it revolves around the sun. So it's literally spinning like a top, except on an angle, 23.5 degrees, as it revolves around the sun. Okay? All right, back to 7273. So we continue talking about centripetal force and what's provided by it. Math. So we have this. This is not given to you. What is given to you on the formula sheet? What is actually given? This is not given. Zoe? No? I thought you were about to raise your hand. What is actually given to you on the formula sheet? Come on, people. Look at your formula sheet if you have to. Yeah, that's what's given you right there. And this is the center-seeking or centripetal acceleration. That's what's pulling the object toward the middle, the acceleration. Well, that is because of a force. How do you find force, though? Force equals mass times acceleration. So literally take this and multiply it by mass. So this equation up here is not given to you, but you know acceleration, just multiply it by mass and you get the force. Depending on the problem, Fc takes on many possible values. If I'm spinning something like this, the tension in the rope goes into Fc. Remember, if an electron is orbiting, it's the electrostatic force that would go in there. So depending upon the scenario, a different value may or may not go in here. Vt is what again? Vt? Tangential velocity. Okay. R is the radius of the circle. M is the mass of the orbiting object, or the object that's revolving. R has 3 definitions for this test. Let's make sure we understand all 3 of them. That's the first one. Okay, R in this formula is radius. How about in this formula? How about in this formula? So in the first formula, R is the radius of the circular path that the object travels in. What's R in the second formula here? What's R in the second formula? What is it defined as? Look in your notes if you have to. This is 7273. You should have this written down. What is R defined as when we look at the gravitational force between 2 bodies?
It's the distance between the 2 centers.
Yeah. R is the center-to-center distance. Now, how do I draw that? If I have the sun here and the earth out here, and I want to know how far apart their centers are, I have to consider the radius of the sun, and we did this, plus the gap, plus the radius of the earth. Again, R is the radius of the sun, plus the gap, plus the radius of the earth, add them all together, that goes in for R right here. So R has a second meaning right there. Well, there's a third meaning to R now. We did torque, which, by the way, God bless you. Torque is not on your formula sheet. I thought it was.
Yeah, it was.
It's probably on the electronic version you guys have downloaded. It's not on the laminated one. So when you take the test, I'll put the equation on the board. I'm not going to relaminate them all. It's not worth the time. Maybe eventually I'll do it, but not this year. So the torque involved here, if you remember, is R, F, sine theta. What's R in this case? So the first R was radius. The second R was distance from center to center. What is this third R? What does R represent for torque? Torque. Come on, somebody else. Same 2 people are answering a lot of questions. What is the other R value? What does R stand for in torque? If you don't know exactly, tell me. Explain to me. Ellie, explain to me, what is R for torque?
Isn't it like, it's not distance, but isn't it something like it's like,
It's measured in meters, so it is definitely a length.
oh, is it like the radius, but,
It's not a radius. Klaus?
I was gonna say distance.
From where to where, though, Klaus?
From the center to the, I guess, circumference.
To the what? What was the last part?
Like the outside, I guess, circumference.
Well, if you have like you had the example, if you have a force acting on, if say that's like a piece of wood, and then the center, like how we have the thing, it's the distance from the center to the force acting on it.
The center or
Or like wherever the,
pivot?
that.
It's the distance between the pivot or the axis of rotation and the force applied. R is the distance between the axis of rotation and where the force is applied. Theta is defined as the angle between the force and R. There's theta right there. Yes, no.
Sorry.
That's all right. Just the way you like went to stretch, it looked like it was like an
I
all.
know, sorry.
All right. What else do we want to go over? What questions do you have for me right now? What questions do you have for me right now?
Can we go over a homework question?
Sure. Whichever one.
One on.
I'm always happy to do homework, by the way. We don't usually review homework in here, but if you ever have questions, anytime, yeah.
It was the
Read it to me. Go ahead.
oh yeah, page. Oh, I don't have that in my textbook.
Sure.
Okay. So it was like they gave you a diagram.
Oh, was this 8-6?
Yeah, it was 280.
I'll give you a hint. Is it this one right here?
Yeah.
I'll give you a hint because I don't want to give away the answer. This is one of your problem set questions also. I chose it for problem set as well. So what is this, page 282, number?
Yeah, page 282, number 3.
And it's at the bottom, right? 3 on
Yeah.
the bottom? So let me give you a little hint. Maybe somebody could help. You're given a bunch of stuff. You're given a point here, a point here, a point here. But they call this point O, and they say it revolves around O. So if you want, when you're doing this, you don't need to draw these. Those are not necessary. Okay, they put points there to show that the force acts at that exact location. But you don't really need those points because it's very misleading. It makes it look like a pivot. The pivot is on the left. Okay? Now you have a force acting from the top up, over here like that. And you have a force acting down and out like this. Here's my hint. They give you this angle. What is this angle? 31 degrees, right? They give you that angle, but that's not the angle you want to use. Okay, remember, that's not the angle you want to use. They also give you a force here. Oops. They give you a force down here. They give you this angle. That is the angle what is that, 23? No.
23, yeah.
That is the angle you want to use. Then they give you a last force, which acts on or at the rotation. I'm not even going to label that. Why do we even care about the force or the angle there?
Oh, because it's automatically 0. If you're pushing it at the hinge, you can't do anything at that point.
At the hinge, you get no torque.
Yeah.
What's R at the hinge? What's R at the hinge? 0.
So anything multiplied by 0, it doesn't matter. The angle can be as large or as small as you want. Anything times 0 is going to be 0.
So when I push, remember we talked about this? If I'm literally on the hinge, I can't do anything. Like I'm trying really hard. I'm actually on the hinge. I'm barely stopping.
If you're listening right now, he actually
Okay.
went on the hinge.
So you really can if you're actually on the hinge. My hand's not going to crush. But if you're actually on the hinge with no lever arm, no leverage, lever arm, you're missing that. So R is 0 in this case. R here is whatever this distance is. R for this one is whatever this distance is. So that's my hint I'll give you. Okay? The rest of it you should be able to do. Look at the last 2 examples in 8-1 that we did in class. Good question. I've been asking these questions all year. What happens if the radius of an object in circular motion doubles and the mass triples? What happens, you can write it down if you want, if the radius, what happens if the radius of an object in circular motion doubles and the mass triples? What happens if the radius doubles and the mass triples? So what do I do? What do I do in the formula? Ellie?
You just put a 2 in front of the R and a 3 in front of the M.
So how does the overall force change? By what factor?
5.
Just literally read the numbers. By what factor?
5 factor of 6? No.
How do you say 3 over 2? What's the mathematical way to say that?
3 halves.
3 halves. It goes up by a factor of 1.5 or 3 halves. That's an easy way to do it. How about this one? What if the velocity doubles and the radius triples? New one. What if the velocity doubles and the radius triples? So radius triples, and again.
Would it increase by 4 thirds?
4/3, very good. Velocity doubles, let's do this first at the top, and the radius triples. When you double the velocity though, you need to remember that you have to square the velocity, so 2 squared becomes 4 in the numerator, and since the radius tripled, you have 4/3 now.
Didn't you say triple and half?
I just said it, let's do a new one, I said, yeah. So the new one was what happens if
It
the...
was like wrong, okay.
What happens if the velocity doubles and the radius triples was the new one. Okay, so it becomes 4/3 of the original. That's what it becomes at the bottom down there. You could do this with any formula, right? We know that you can do any formula throughout the year. So it could happen with gravitational formula, it could happen with your torque formula. I could say, what happens if the force you apply doubles, but you have half of the lever arm? How about that one? Answer real quick. That could be a multiple choice. The force doubles, but your lever arm is cut in half. What happens to the amount of torque you provide?
Doesn't it just stay the same?
Stays the same. You did it, thank you. You double the force, but you have the lever arm. So you have 2 times 1/2, really. Okay, again, I'll write that out so anyone that's confused can see that. If you double the force, here's our formula, RF sine theta. If you double the force, and then you have the lever arm, you get this. Half the lever arm, double the force, angle wouldn't change. Well, what's 2 times a half is just 1. So in the end, what happens? There's 1/2 and there's 2. They just cancel each other out. So if you have the lever arm and double the force, nothing happens. We did that in the first example of the lesson for torque. Okay? What happens as the angle goes from 90 degrees to 0 degrees? What happens as the angle goes from 90 degrees to 0 degrees? What happens to the torque? 90 degrees to 0 degrees. Kate? The torque decreases. Again, imagine some sort of a wrench. Here's the head of the wrench right here. You apply a force on that wrench perpendicular to it. You get a lot of leverage. You get a ton of leverage by pushing this way. But instead of pushing at 90 degrees, what if I push at like 2 degrees, like that? Am I going to do anything? Is this going to rotate easily? No. If anything, I'm going to push the wrench off of the bolt or off of the nut, whatever it is here. So 90 degrees gives you maximum torque. 0 degrees gives you 0 torque. Okay? So if I push like this, the vector in white that's pushing to the right from the end of the wrench will not rotate it. What will it do? It'll remove the wrench. If you pull back on the wrench, you're going to literally remove the wrench from the bolt. But you are not going to cause a rotation from that white vector there. You should know Kepler's laws, but you do not need to regurgitate them. But if I asked you about them, you should be able to recognize them. Okay, but it will not ask you to state the 3 laws. Okay, but if I asked you a question involving the 3 laws, you should be able to understand what they are. You don't have to state them word for word. We talked about a lot of stuff. We talked about, in the 3 laws, about the seasons we talked about of the year. We talked about the area swept out, when the earth is traveling faster, when it's traveling slower. What else? Your mathematical questions, you have pretty much 3 formulas you could expect. FC equals mv squared over r. Fg equals gm1 m2 over r squared. And tau equals r sine theta. Those are the 3 kind of problems you could expect mathematically. I'm trying to think if there's anything else I want you to know beforehand. What other questions might you have? Yeah?
What was the reason for the seasons? Was it just because which
hemisphere is facing? So here's the Earth, here's the Sun. What, did you trick her? You asked her?
I explained it to her, and she did the typical answer, and then I tried to explain it to her, and she was like, no, it's not. And I was like, yeah.
Oh yeah, it is, for sure. So here's the Earth, right? Here's the poles. Here's the northern pole, here's the southern pole. So over here, when we're further from the sun, all the way over here, in the northern hemisphere, look at all the northern hemisphere right here, faces the sun. This is rotating like this, over and over. So this southern half is not facing the sun as much as the northern half. So we get longer days and more direct sun rays when we're further from the sun in the northern hemisphere. When we're closer to the sun, we get shorter days in the northern hemisphere. It's the opposite for the southern. Yeah.
Also the question where it said, does the Earth travel faster when it's closer to the sun? It does, or?
It does.
When it's because of the gravity, right?
Not really.
Is the gravitational pull, or?
Oh, sure. You could think that the distance is closer, but remember this law, one of Kepler's laws, talked about swept out areas?
Oh, right.
Look at that area. Shade that in. That area is probably the same thing as that area. Even though it doesn't look like it, one is like a long sliver, the other one is like a short, wide area, but those are approximately the same areas. Let's assume they are, okay? Which they really are pretty close. Look at the distance traveled when it's further from the sun. It only travels a little short arc length. And that takes, let's say, hypothetically a month. But when it's closer to the sun, on the left-hand side over here, it travels this much longer arc length in the same time period of a month. So if it travels much further in a month over here than it travels over here, the speed must be greater over here on this side.
So is it another example where angular velocity is the same but tangential is different?
No, because it's not in circular motion. Remember?
Oh, right, yeah.
Angular velocity can only really be true in circular motion. The minute you have an ellipse, there's no longer angular velocity involved. I know you're tired, guys. I can see it. I'm tired also. Try to bear with me. I'm seeing a lot of drowsy eyes. What else? Day 3 is my longest day for sure. Only because I don't teach much in the morning, and then I have 4 periods at the end of the day. I had double in physics before this. I had math. It's just a long day for me.
And it's also exam.
Yeah, that exam.
Do you only teach freshman class?
Yes.
Isn't the freshman class really small this year?
What I teach?
Yeah.
Well, there's 2 sections. There's 2 honor
There's
sections.
2 honor sections this year?
So I would teach some of them. So
Well,
last year,
only have 1.
last year, no, it was also 2 the year before that when I had you guys. It was only 1. We had what?
Yeah, we had
18 or 19?
Oh, I don't know.
Remember the demo lab, or not demo, the experiment lab you guys did where you hang the masses off the little ruler or whatever that was? The theory behind that you should understand, right? So if I move further out, I get more torque. If I move further in, I get less torque. If I hung the mass right in the middle, would it do anything? No, because it's not providing any torque. It's on the axis of rotation itself. I should have done that, but I realized that after. Remember I put all those hooks? Those little S hooks I put everywhere? I should have put a hook right in the middle. I think I'm going to do that for next year. So if people try that, they'll recognize by putting anything in the middle, it doesn't spin either way because R equals 0 when you're in the middle. There's no left one. It's R value. What other questions might you have? Homework, problem set questions you can stump on. No, nothing? No? Trying to think what else I want to go over, but I've covered everything that's on the test. And I'm looking at the test I wrote, so that's why I'm saying. No?
Yeah, let's see it, please.
Nice.
No.
Can we just stand just for a second?
Press
No.
the button that makes it go on the screen.
Oh, here's a question. So you should be able to calculate tangential velocity if you know the radius and time like you did in the lab. So let's discuss this real quick. So an object moves in circular motion. I want to figure out the tangential velocity as it moves. Let's say that the radius equals 2 meters. And I want to find the tangential velocity. And I tell you that it takes, I don't know, 1.8 seconds to complete a revolution. How do I find the tangential speed or velocity?
V equals, what is it, T over T?
Yeah. Speed equals distance over time. What's the distance traveled? Remember, you're really looking for speed here, not velocity. Circumference. Okay, remember that. I know that's geometry, but clearly in physics you do use geometry. Okay? So you need to know your laws of geometry. 2 pi r over time will give you the answer for the speed. That's this right here. I know I used S and VT. It really is tangential speed in this case, because after a revolution, the velocity would technically be 0. Because if it ended where it started, it has no displacement. We did a Tarzan example. Do you remember that? You don't need to know that example, and it was a little bit complicated, but you should understand the idea of maximum allowable force. So if I spin something on a rope and the rope snaps, what does that mean? I'm spinning it, I'm spinning it, I'm spinning it. The rope eventually just snaps and the object shoots off. What conclusion can you draw?
That the force applied outdid the maximum tension of the rope.
Exactly. The maximum tensile strength of the rope was exceeded by the amount of centripetal force that you gave. Again, spinning too fast, centripetal force goes way up. It goes up beyond the FT max, the tension force, the maximum allowable. So as a result, the object will rip the cord and shoot off some direction around it. Trying to go through some theoretical stuff with you guys. For mathematical, when you do torques, you can absolutely 100% expect an example like the last two that we did. The one that we did yesterday, and then the one that we kind of started the day before and finished yesterday. So where you have a rod, like the one that's for torques, for the math part, you could expect something for sure like this, where there's a force maybe here, here, and here. Maybe I'll ask you, what's the overall net torque? And all you have to do is find each torque, either apply negative or positive sign, depending on if it's clockwise or counterclockwise, and then solve. Or, I might say, find the R value, or find the force needed in one of them, I'll give you everything else, so that it provides rotational equilibrium. What does that mean? What does rotational equilibrium mean? Or so that it, what does rotational equilibrium mean? Rotational equilibrium. If I do this, let me give you an example. This is currently in rotational equilibrium. Okay, now watch. If I do this, and it falls, it's not in rotational equilibrium. What is rotational equilibrium? Emma?
Like when the forces on the either side of
The fulcrum.
the fulcrum, when they are
When the torques. When the torques are equal or opposite, when they balance. So sum of the torques equals 0 for rotational equilibrium. Rotational equilibrium implies that it's not moving. It's not moving. If you get an overall net torque, it means it is moving. Okay, again, recording tomorrow in the other class, so feel free to watch theirs. Noon tomorrow for problem sets. Noon.